Over the last 4 episodes, we built the complete generative stack: SDEs for continuous time, score matching for training, flow matching for efficient transport, and guidance for control. We treated this as a way to generate images. But here is the secret. The math doesn't know what an image is. Look at the fundamental SDE. dx equals drift times dt plus diffusion times Brownian motion. There is no variable here for pixel or color channel. This equation simply describes the transport of a probability distribution from noise to data. This implies a powerful generalization. If you can define a distribution over a data type, you can diffuse it. Today, we stop generating pixels. We are going to generate life-saving drugs, protein structures, and robot behaviors using the exact same engine.
Let's start with biology. AlphaFold solved the forward problem, predicting structure from sequence. But we want the inverse, designing a structure to perform a function. This is what Watson et al.'s RFdiffusion does. But a protein isn't just a point cloud. That's too loose. A protein backbone is a chain of rigid bodies. Each amino acid residue has a specific coordinate position and a specific orientation. Mathematically, this lives on SE3, the special Euclidean group. It combines translation in R3 with rotation in SO3. When RFdiffusion adds noise, it doesn't just jitter the coordinates. It performs a random walk on the rotation manifold. It corrupts the orientation matrices. The reverse process must predict how to translate and rotate these frames back to a valid low-energy state. This allows us to hallucinate proteins that have never existed in nature, yet are physically valid enough to be synthesized in a lab.
Small molecules pose a different challenge. A drug molecule is defined by atom positions and discrete atom types: carbon, oxygen, nitrogen. Here, we face a strict physics constraint: symmetry. If you rotate a caffeine molecule 90 degrees, its chemical properties remain identical. Standard neural networks don't know this. They see a rotated input as a totally different object. To fix this, Hoogeboom et al. Introduced equivariant diffusion models using E3 equivariant networks. This guarantees that if you rotate the noisy input, the network's predicted vector field rotates in perfect lockstep. Furthermore, they run dual diffusion processes. The positions diffuse with Gaussian noise in continuous space. The atom types diffuse by randomly swapping categorical identities. The model learns to denoise geometry and chemistry simultaneously, respecting physical symmetry at every single step. Now, let's move to robotics. Traditional reinforcement learning policies are often unimodal. They try to output the single average best action. But suppose a robot needs to go around a tree. It can go left or right. The average of left and right is straight ahead, crashing directly into the tree. Diffusion models solve this naturally because they model distributions, not point estimates. Chi et al.'s diffusion policy represents the robot's plan not as one action, but as a trajectory, a sequence of actions over time, typically 8 to 16 steps into the future. By diffusing on this trajectory space, the model captures the multimodal distribution. It represents go left and go right as distinct modes. During inference, the reverse process collapses the noise into one specific, valid path, avoiding the fatal average. This trajectory view unlocks something incredible. Planning becomes inpainting. In image diffusion, if you mask half an image, the model hallucinates the missing piece. Generative et al.'s Diffuser applies this to physical planning. A trajectory is just a tensor of states, state 0 through state t. If you know where you are, state 0, and where you want to be, state t, you can simply clamp those values in the noise tensor. You then let the diffusion model inpaint the steps in between. You don't need a complex search algorithm like A*. You treat the path from A to B as a missing data problem. The model fills in the physics and collision avoidance automatically, connecting your start and goal with a valid execution plan. Finally, we reach the hardest modality: text. Images and robot paths are continuous variables, but you can't have 0.001 of the word apple. Text is discrete. We cannot use Gaussian noise here. Instead, we use transition matrices. We define a corruption process Q sub t, where at each time step, a token has a probability of flipping to a random token or a special mask token. This drives the text toward a uniform distribution of random gibberish. The reverse process is trained to predict the original token from the corrupted state. This is discrete diffusion. Unlike GPT-4, which generates left to right, discrete diffusion generates holistically. It refines the entire sentence at once, allowing for bidirectional context and global coherence that autoregressive models struggle to achieve.
When we step back, the pattern is beautiful. For images, X was a pixel grid. For proteins, X was a set of SE3 frames. For robots, X was a trajectory tensor. For text, X was a sequence of categorical indices. But the algorithm remains the same. Define a forward process that destroys information. Train a network to reverse that process. Use that network to generate structure from chaos. The domain knowledge only enters in two places: the choice of state space and the symmetries of your neural network. Everything else, the SDE, the flow matching, the guidance, is universal.
We are seeing the same scaling laws apply here as in language models. More compute and data lead to better physical understanding. We are moving toward scientific foundation models, single models trained on massive datasets of molecular dynamics, DNA, and climate data. These aren't just simulators, they are generative engines for discovery. We've moved from making pretty pictures to designing the machinery of life itself. This concludes our 5-part series on diffusion models. We started with the intuition of denoising. We derived the continuous time SDS. We learned to train them with score matching. We optimized them with flow matching. We controlled them with guidance. And now we've applied them to the physical world. You now possess the complete theoretical stack of the most powerful generative framework of our time. The rest is up to you to build.